Thank you very much.
So, hi everyone. My name is Kanji Mori from National Astronomical Observatory of Japan. And first of all, I'd like to thank the organizers for giving me this chance to talk here. I'm very enjoying the stay in this beautiful city of Firenze. And today I'd like to talk about my recent works about sterile neutrinos from quark-collapsed supernovae. Okay, now it's working. So, as you know, supernova is a source of multi-messenger signals. For example, supernova event is very bright in the point of view of photons. Of course, we have already detected neutrinos from the supernova 1987A. So we know that supernova event can produce a lot of neutrinos. And also, we may be able to detect gravitational waves in the future if supernova event happens somewhere nearby. And this is a standard framework of multi-messenger astronomy, of course. But in theory, supernova event can produce this kind of exotic particles beyond the standard model. And one example is, for example, axions. And I did several works about these actions from quark-collapsed supernovae. And also, supernova may produce sterile neutrinos. And if this kind of exotic particles are produced inside the supernova, then they may affect the multi-messenger signals. So, and in order to study the effect of these particles on signals, then I'm recently developing a supernova simulations coupled with this kind of exotic particles. And anyway, let me talk about these sterile neutrinos in this talk. So this is the contents of my talk. First, I'd like to talk about my recent work about supernova simulations coupled with heavy sterile neutrinos with a mass of around 200 mega electron volt. And in the second part, I'd like to talk about supernova simulations coupled with more light sterile neutrinos with a mass of around 1 electron volt. And in this heavy sterile neutrino part, I have already written a paper and it is already accepted. And as for this second part, this is only this project is still ongoing. So I can show you here only very preliminary result. But anyway, let me discuss also this light sterile neutrinos as well today. So let me start from this heavy sterile neutrino part. So sterile neutrinos are right-handed neutrinos, so they do not participate in the standard weak interaction. And the motivation to introduce this kind of the heavy sterile neutrino is that if they really exist, then they can give the light neutrino masses to the so-called seesaw mechanism. And this sterile neutrinos can mix with active neutrinos like this. And of course, they could mix with, for example, electron type neutrinos or muon type neutrinos. However, in this first part, I would like to discuss mixing with tau neutrinos because mixing with sterile and nu e and nu mu has been explored by, for example, terrestrial experiment. But it is difficult to investigate this mixing with tau neutrinos, and we will see that supernova is a very unique tool to study this mixing of sterile and tau neutrinos. So this is our current parameter space for this nu s nu tau mixing. So this is a parameter space. So vertical axis shows the coupling constant. This horizontal axis shows the mass of sterile neutrinos. And for example, this red region is excluded based on the 87 energy loss argument. And also the left-hand side of this green curve comes from is excluded from the Big Bang nucleosynthesis, but this right region is still open. And actually, in this study, I am now exploring this region, and we will see that if sterile neutrinos are really in this region, they can significantly affect the supernova dynamics. So, yeah, and this affects the signals from quark-collapsed supernova event. However, this kind of the multi-dimensional simulations coupled with this heavy star neutrinos have not been performed. So this is what I did. But for 1D simulation, there is a very pioneering work here. So and heavy star neutrinos inside the supernova are produced through this kind of processes. So basically, they are produced by the pair annihilation of active neutrinos. And the amplitude for these processes can be written like this. So in principle, we can just calculate the collisional integral using this amplitude. However, it is very, in order performing this collisional integral inside the supernova simulation needs very high computational cost. So in this study, we don't do it. Instead, I adopt this fitting formula for the action production rate produced by this study. So in this study, this formula is used. And one interesting point is that this kind of heavy star neutrinos decays inside the star. So if the heavy star neutrino mass is heavier than the pion mass, then this decay channel into pion is open. And if star neutrino is decays into pion, then this pion will immediately decay into 2 photons like this. And then these photons will be immediately thermalized with surrounding material. So this decay channel will due to additional heating rate. And also, this active neutrinos are also produced through this decay. And this neutrino will escape from the star. So this will be, in principle, detectable as a high energy active neutrinos. So in this study, we discussed the effect of both of these daughter particles. And the decay length of this neutrino, cell neutrino decay is estimated like this. So you can find that this decay length is very dependent on the star neutrino mass. So if the star neutrino mass is heavy enough, then the decay length becomes shorter than the stellar radius. Yes, please. No, in this study, we just consider these processes. In this case, the mass is too heavy. So I think, for example, if we consider the wave packet of mass eigenstate and the the this heavy stellar neutrino is not a relative stiff particle. Yes, that's right. Yes. Excuse me. Energy of stellar neutrinos. New tau. New tau is around, let's say, 110 mega electron volt. Transition. Oscillation. This daughter active neutrinos will, of course, experience, for example, MSW effect. Mhm. So you mean that this could oscillate into star neutrinos as well? I see. Uh, かな。Mhm. I see. So in this study, I have not considered the possibility of the oscillation between this neutrino and stellar neutrinos in the outer layer. Yeah. And this is a setup of our simulation. So we use a supernova simulation code called 3D NSN code, which have been developed by Japanese supernova modelers. And I performed 2-dimensional simulations. And for now, I fixed the Ponzeta mass to the 20 solar mass model. And what I solved for the star neutrino is this. So this is a zero angular momentum of the Boltzmann equation, and here E is sterile energy density, and F is flux, and I just solved this within the ray-by-ray approximation. And once we solve this equation, we can obtain the heating rate at each point. And I just use this heating rate induced by the sterile neutrino decay and cooling rate induced by sterile neutrino production to modify the internal energy at each point. So before going to the result, I wanted to briefly explain the explosion mechanism of core collapse supernova, but today we have already enjoyed a very comprehensive review of this topic, so I think I can skip this part. But in this study, I focus on the this part after the just after the core bounce, because at this phase, the central density is the highest, so the sterile neutron luminosity could be the highest. So, this phase could be the most interesting part for our purpose. So this is our result. So the left panel shows the model without sterile neutrinos, and the right one includes the effect of sterile neutrinos. And so please focus on the difference between the two models. And this, you can see the discontinuity here. This is a bounce shock. And after several hundred milliseconds, the bounce shock, starts going outward. And you can find that if we include the effect of sterile neutrinos, then the radius of bounce shock becomes larger than the standard model. This is because of the additional heating rate induced by the sterile neutrino decay. So you can see that sterile neutrinos, heavy sterile neutrinos can assist the supernova explosion. So this is the shock radius and the explosion energy for the model. So the left one shows the shock radius as a function of time, and this black curve shows the standard model without sterile neutrinos. And the other models include the effect of sterile neutrinos, and we change the coupling constant. The mixing angle. And you can find that if we include the effect of sterile neutrinos, the shock radius becomes larger, as we have already seen. And the right panel shows the explosion energy as a function of time. And you can find that if we increase the effect of sterile neutrinos, then the explosion energy becomes higher. And actually, this horizontal line is a so-called 1 beta, which is equal to 10 to 51 L. So you can find that if we increase the effect of, we increase the mixing angle, then the explosion energy exceeds the typical value of observed type 2 supernova. And I believe that this kind of model is obviously against the, the current supernova paradigm. So I think that this kind of high mixing angle should be excluded through the this explosion energy. So why does this happen? So this shows the extra cooling rate and the extra heating rate as a function of radius. And these thin lines correspond to cooling rate and heating rate induced by active neutrinos. And these thick lines correspond to additional rate induced by sterile neutrinos. And you can see that the contribution of sterile neutrinos is still lower than the active neutrinos. But this kind of 1% contribution to the heating rate still makes changes. So this is a neutrino signal induced by this daughter tau neutrinos. So the left panel shows the anti-tau sterile anti-tau neutrino spectrum, and this black line is a standard thermal spectrum. And you can find that if sterile mass is around 150 MeV, then unfortunately the energy of this daughter active neutrino is not so high. So this is much lower than the standard contribution. However, if the mass of sterile neutrino is large enough, then the contribution of this decay neutrino actually exceeds this thermal contribution. So assuming the hypercamiocan, we estimated the event number, and here we assume that the supernova is located at the galactic center. And you can find that the event number exceeds 1 if and the neutrino energy is around 150 MeV or so. So if we observe this kind of high energy neutrino bump, then that could be a smoking gun of this kind of exotic particles. So finally, I estimated the gravitational wave signals. So this is the left panel shows the waveform of gravitational waves, and you can. It is a little bit difficult to see, but if we increase the mixing angle, the amplitude of gravitational waves becomes a little bit smaller because this heavy stellar neutrinos produces extra heating rate, and this prevents the mass accretion on the proton neutron star. And the right panel shows the spectrum of the gravitational wave. So unfortunately, the difference is not so large between the models, but among the models. But anyway, in this parameter region, the gravitational wave signals is above the current sensitivity curves like this, if the supernova is located at the galactic center. So that was the heavy stellar neutrino part. So in the second part, let me discuss the lighter stellar neutrinos with a mass of around 1 electron volt. And the motivation to introduce this kind of light stellar neutrinos is this reactor anti-neutrino anomaly. So this is a electron anti-neutrino flux from reactors as a function of distance. And this red curve is a prediction for the standard 3-flavor oscillation. And if they include one flavor of stellar neutrinos, then the prediction becomes a little bit smaller. And and as a result, the fitting between observation and theory becomes slightly better. So this deficit in the reactor neutrino flux could be a hint of another flavor of stellar neutrinos. And this is a current parameter space for this light stellar neutrinos. So this vertical axis is the mass of stellar neutrinos again, and this horizontal axis shows the mixing angle. And these blue islands are the preferred region for the that comes from the reactors. And there are other constraint and some preferred region like this, and combining these electron type neutrino disappearance experiments, preferred region becomes like these red islands. And the current experimental best fit parameter is written like this star, and which corresponds to this parameter. And we will see that if stellar neutrons really exist at this point, then there could be an impact on supernova dynamics. So this kind of light stellar neutrinos could be can be produced through the MSW effect, and the MSW resonances will happen if this resonance condition is satisfied. And the left-hand side is a vacuum component of the Hamiltonian, and the middle one is matter potential. And in this parameter space, the value for the left-hand side is much smaller than this GF times baryon number density. So this resonance condition is satisfied when the electron fraction is equal to 1/3. So this is very schematic picture for the situation. So if electron type neutrinos comes across this isosurface of y equal 1/3, then a part of stellar neutrinos could be a part of nu e could be converted into stellar neutrinos like this. And actually, this MSW resonance is not so adiabatic. So we can use this Landau-Zenner formula to estimate the conversion probability here. And if really this happens, then this could reduce the active neutrino flux in the gain region. And as a result, this will reduce the neutrino heating rate in the gain region. And So this could affect the supernova dynamics, and also, of course, there should be some effect on neutrino signals. So this kind of possibility has been actually discussed by several previous works, and this is one result. So in this study, they adopted this parameter here, and in this study, they estimated the the neutrino heating rate in the green region as a function of radius, and with the post-process technique, and this red curve comes from the standard model without star neutrinos, and this blue curve comes from the model with star neutrinos. And you can find that the heating rate is significantly reduced. So when I saw this panel, my question was this: so in this situation, do supernova explode at all? So in order to answer to this question, I am now performing two-dimensional simulations coupled with this, oscillation between active and star neutrinos. So this is again the setup. So I'm using the same code as the previous study, and I'm now performing one-dimensional and two-dimensional simulations. And as for the progenitor, I adopted this 14 plus 9 solar mass merger model, and this star model is fine-tuned to reproduce the nature, observed nature of supernova 87A progenitor star. So here we call this model supernova 87A progenitor model. And as for the star neutrino